Hey everybody, so in this video we're going to just go through the start of the heat and temperature topic for people who were absent for different reasons at the start of the year. This video will mainly just cover the theory, and I'm going to put up a separate video that will cover the specific heat capacity and heat capacity calculations to catch everybody up till that point at least. So we're going to try and go through this pretty quickly. If you do have any specific questions on different topics within this, just ask me in class or send me an email and I'll try and get back to you. So the main thing to know about heat is that heat is the addition or removal of energy from a body. If you want to take that down into your notes. You might remember from junior cycle they had the different forms of energy: light, heat, kinetic energy, which is movement energy. But heat is one of those forms of energy, right? There's about 10 of them altogether. And when you add or remove heat energy to a body, it either increases or decreases the temperature of the body. I'll have to excuse my handwriting here. So it either increases or decreases the temperature of that body. What I have written over here on the side is just 4 marks and 3 marks. Very often in a definition in the Leaving Cert Physics exam, they'll give you 6 marks or 7 marks, and you can see on the side, normally they come in bundles of about 3. So if this was a 7 mark question, it might be 4 marks for the basic concept, then 3 marks for the more detailed explanation. So 4 marks for saying heat is the addition or removal of energy from a body, and then 3 marks for saying in such a way that it either increases or decreases the temperature of that body. So if heat is a form of energy, then if we add heat to a body, it can alter its temperature. So the temperature of a body is a measure of how hot it is. That's our basic definition. So hotness is actually a word that comes up in the course, believe it or not, when we're talking about temperature. Temperature is a measure of the hotness of a body. And the temperature can be affected by adding or removing heat energy, but the relationship isn't completely linear, as you're going to see on a graph now in a minute. Both of these definitions, by the way, are very important for heat and temperature. So before we look at that graph, let's just recap what happens when we heat solids. So if we start off with solid particles here, all the particles are kind of in a fixed position. They can vibrate around, but they're not going to be able to flow around each other. As we heat them up, we're adding energy. We call that process melting when a solid turns to a liquid. So liquid particles are able to flow around each other. They're still going to be beholden to the laws of gravity, so they'll still fall down to the bottom of their container, but they will take the shape of their container. So if you put them in a saucepan, the liquid will flow out and take the shape of the bottom of that saucepan at least. Heat that up a bit more and we get a process called evaporation, sometimes called boiling, but boiling is a little bit different. So evaporation is when it changes from a liquid to a gas. Now the particles have even more energy, so the particles aren't beholden to gravity anymore. They're able to get up and start flying around the place. They take the full volume of their container. So if they're in this box here, for example, they've been knocking off around the edges and trying to take up as much space as they can. If we reverse those processes, so we get a gas and we remove energy, we call that condensation. And if we go from a liquid to a solid, we reverse again the process of melting and we call that freezing. I'm sure you're all familiar with a device that does that in your house called the freezer. There are a few exceptions to this, but none that are on the course. So for example, you can go straight from a solid to a gas in some very specific situations, and that would be called sublimation, for example. But these are the only state changes that are on the course. Make sure you know the keywords related to them. This diagram should be very familiar to you from doing your cert. There's a good simulation that you can play around with to try and visualize what's happening during those processes. So if you would like to do that, click that link there in the PowerPoint. It should be up on Schoology, and you can have a bit of a mess around with it. You can heat up things to try and make them melt or evaporate, and then cool them down to try and reverse those processes into condensation and freezing. Now Now I mentioned a couple of slides ago that as we add heat, I'm going to get you to ignore this part here about time. It does make sense, but we don't really need to think about it. So as we add heat to a body, so the amount of heat in the body is increasing, the temperature will generally tend to increase, but it isn't always the case. So heat is a form of energy, and it can increase or decrease the temperature of a body, but the temperature is kind of independent sometimes. So an example of this would be if we look at ice, and we have some ice here that's very, very cold. We heat the ice up and it gets to, because it's water, temperature of 0 degrees Celsius usually. It'll stay at this temperature for a while. So even though we're adding heat energy along this section here, the energy is increasing. The temperature here doesn't actually go up like we would expect it to. It's able to absorb energy as it changes state. Once it has changed state, then adding more heat energy will cause the temperature to increase or go up again. But then we end up in a similar situation here when it wants to change state again, changing from a liquid to a gas. So it's not a really clear-cut process as I guess we intuitively imagine, but they certainly are related, but they're not the same thing. Certainly one really important way that they differ for you guys is that heat is measured in joules because it's a form of energy, and temperature on the course will be measured in degrees Celsius or Kelvin, which is an alternate temperature scale. So we need to know about thermometric properties for the course. You can see the definition here. A thermometric property is any property of a body that changes measurably with temperature. For anybody who's into language or words or anything like that, thermo means something to do with heat, and metric means something to do with measurement. So these are properties that we can actually use to measure the temperature of a body. So again, these properties are going to change depending on the temperature, so we can use those thermometric properties to measure the temperature. Now there's a few of them you need to know. Some of them you'll probably be familiar enough with already. Some of them might be kind of new and exciting, or maybe difficult to understand. Certainly at least one of them will be. So a thermometric property is any property of a body that changes measurably with temperature. So our examples of this are the length of a column of liquid in a tube. We're all familiar with a thermometer that has a just a small well of alcohol or mercury or something at the bottom. It's got a liquid at the bottom, and then the body of the thermometer kind of encapsulates that. As it gets hotter, the length of this column of liquid will increase. As it gets colder, the length of the column of liquid will decrease. So that's the thermometric property you're probably all pretty familiar with. The resistance of a wire or a thermistor is the second one. So if you get a wire and you measure its resistance using some kind of ohm meter or digital multimeter, which you'll learn more about next year. Essentially, just if you measure its resistance, that resistance will change depending on the temperature. That's also true for a piece of equipment called a thermistor, which has a much more noticeable effect. It's designed really, most of the thermistor's applications are just to measure temperature in an electric circuit. So the color of some substances will change with its temperature. I'm going to show you an example of that in a second, but children's thermometers are a good example of that. The pressure and or volume of a fixed mass of gas. So if you, for example, have a bunch of gas particles and you heat them up, they're already exerting a certain amount of pressure against the outside. If you heat them up more, they're going to move around more, so the pressure they exert on the outside will increase. Or, for example, if they were in a balloon, they might be able to increase their volume because of all this additional energy that they have to push against the outsides. And then the final one there is the electromotive force of a thermocouple. This is an awkward part of the course because you don't really learn anything about thermocouples on the course, but they want you to be able to discuss it as a thermometric property, even though you don't know anything about it. There's no other background info on the course, so I'll go through that now in a second, which is, and I also want to show you the colour of some substances, how that changes. So this is a type of thermometer that I certainly had in my house when I was a kid, because I think when you have a kid, you probably don't want to be sticking a thermometer in their mouth when they're sick. They'll be getting cranky at you, especially if it's a baby or something. They certainly will not understand what's going on when you stick something in their mouth. So you can use a thermometer that looks like this. There's different strips here that are filled with special substances. I think they're types of crystals. And if it's 35 degrees or over it, this strip will light up. If it's 36 degrees or over it, this strip lights up. If it's 37 degrees or over it, this strip lights up. And then you can see this person here, their temperature is pushing 38 because this strip here is starting to light up. So you can measure that person's temperature using something like that. It lights up depending on what the temperature is. People will also buy stuff like this if they're fermenting foods or fermenting drinks. They can put a strip like this, stick it on the side of the fermentation vessel. If you want to have the thing fermenting at a particular temperature, you can just really quickly read it, because it'll tell you what the temperature inside the vessel is without you having to dip a probe into it. Okay, on to thermocouples. So again, look, this is not going to make a huge amount of sense at the moment. Even the term EMF, you won't know until next year, but EMF is essentially the voltage in a circuit. That's a simple way of explaining it. You've definitely heard the term voltage at junior cert before. A thermocouple then is two dissimilar metal wires, so wires that are made of two different metals. You can see they're joined together in two different places. So we have one junction here that's cold, and we have one junction that we want to measure the temperature of. So we keep this one constant, and this can get warmer or colder. And a reading here at the voltmeter will go up or down depending on what the temperature is where the thermocouple meets. So you can see there's an explanation here. I would know the diagram. I believe they have asked about that at least once before. Again, I don't really know why it's on the course. Sometimes they just sneak little bits like that in there that just don't have a huge amount of supporting material behind them. But the course is kind of old, and I think they're looking at updating it soon. So a thermocouple is comprised of two different metals joined together at both ends to form two junctions. These are two junctions here, two different metals here. You don't have to draw two different colours, just say they're dissimilar. One junction is connected to a liquid of known temperature. So for example, this here could be ice water at 0 degrees Celsius. That's a reference junction. The other is connected to a liquid whose temperature you're going to measure. An EMF will be produced, so if you hook them up to a voltmeter, you'll see that there's a reading for the voltage, right? And that will change depending on what the temperature is. And that's pretty much it. Again, you certainly are never going to see a thermocouple again. We'll discuss EMFs and voltages in a lot more detail next year though. Okay, so here's an exam question that's come up before. Describe why it is necessary to have a standard thermometer. So different types of thermometers, like the strip thermometer we saw, or a mercury thermometer, or an alcohol-based thermometer, or even an electric one that's based off resistance, they're all based on different thermometric properties. So the readings that they give at the same temperature might be slightly different. So by having a standard mercury thermometer, it just means that we can refer everything back to that. We have that like as our gold standard. So even like, for example, the meter, we all roughly know what a meter is. But for a long time they had a single meter that they were holding in some kind of a special temperature controlled vault in France. So that, say for example, if somebody copied a meter stick off another meter stick, and somebody copied a meter stick off that, and so on and so on and so on, if the length changed by a tiny bit every so often, over time that could add up to huge errors, and you could have some meter sticks that are tiny and some that are huge, and nobody really knows what what an actual meter is anymore then, because we're just comparing them to different meter sticks. So for the so they had this original meter that they would consult for reference if it ever became unclear, and we kind of used then a mercury thermometer as our standard. to refer back to for temperature readings. And you do need to know that the mercury thermometer is the standard thermometer as well, by the way. Okay, so this is an experiment that we did. It's pretty straightforward, to be honest. We get an ungraduated thermometer. You can see this thermometer here has no markings on it, but this one does. What we do is we increase the temperature using this electric hot plate, and then at a bunch of different readings we see or a bunch of different temperatures. So we have temperature measured in degrees Celsius, and we had the length of liquid in this thermometer here. So this is our standard mercury thermometer. This would be like an alcohol thermometer or something. We use that length in the alcohol thermometer then to measure it. So we get a bunch of different readings, and what we see is essentially something that looks like this. We've got our temperature here as our final graph, and our length here, and we'll get a graph that looks something like that probably. Again, don't forget your units, but I know it's only a quick sketch, just trying to set a good example as best I can. So you get a temperature that looks like that, and then you can actually use that for reference then as a thermometer. So I could ask you, well, look, what temperature is that thermometer now reading, right? You can put it into an unknown substance. You just check the length of that thermometer. So it could be, 15 centimeters, and we could check, well, that corresponds to a length of 60 degrees Celsius or something, and vice versa. I could ask you, well, at 70 degrees Celsius, what would the length of the thermometer be? You can bring this up here, bring it back over, and it might be 16 centimeters, something like that. So a pretty basic experiment, but we got some nice data for it. If you missed that, just get the method taken down into your book and get the results off one of your classmates. Again, if you have any questions about any of this stuff, just do ask me as well. I'm happy to help you out. There's that's an alternate method. So for this one, you put a metal coil into a substance called glycerol, and we're going to heat that up, and we use the multimeter to measure the resistance. So we mentioned before that another thermometric property other than the length of a column of liquid is the resistance of a metal wire. So we wind this wire around and around and around and around and around to try and cram as much of that wire in there as we can. That way we get a really high reading, or as high as we realistically can get on the resistance from a multimeter. And then we just change our temperature and measure our resistance, how that's affected, and the graph will show up looking kind of like this again. And we can use that graph in the same way. If we have a given resistance showing up on the wire coil, then we can say what the temperature is as a result of it. The sources of error for this one are a little bit different. We used glycerol, which is kind of important. So the point of glycerol is that if the water started getting hot, we get bubbles here, so the heat energy wouldn't be able to transfer to the wire coil as effectively. So by using glycerol, we get a better thermal contact is the term. So the heat energy is able to transfer into this wire coil just that little bit better, and it makes the readings more accurate. If you did then, for example, want to make electronic thermometer using this kind of a method, you just get a resistance reading, and then you use some kind of internal chip to turn that resistance reading into an output temperature that you're going to show on your thermometer graph, and then you've got a digital thermometer. So pretty easily done. This is just a checklist. Once you've done up your graph, check that it has all of these things. I won't go through them now. You probably are pretty clued up on graphs at this stage, I hope, but it's just a quick reminder. When you're writing up the conclusion of your experiment, just refer back to the title. So what was the point? The point of that experiment was to create a calibration curve for a thermometer. So did you achieve what you set out to achieve? And hopefully the answer is yes, but just talk about that a little bit. And then sources of error are kind of important. For any experiment, they'll often ask your method, your diagram, they can ask you to do a calculation with the results or plot a graph. And another common thing they'll ask is your sources of error. So how could you avoid making errors in that experiment? So avoiding parallax error when reading thermometer is a classic one. Anytime you're reading any analog equipment, like rulers or whatever, it's very likely that it's possible to make a parallax error depending on the equipment. So just, that's a good go-to if you're not reading something digitally. And then, as we talked about before, the glycerol ensures a good thermal contact, which you wouldn't get with water. So the air bubbles would interfere in that case. Alright, so then we talk about the Kelvin scale. So this is supposed to be degrees Celsius, but it hasn't turned out quite right on this slide. So you probably know that in our day-to-day lives we use a temperature scale that goes from it goes from 0 all the way up, and it also goes from 0 quite far down. So you have 0 degrees Celsius here. It's based off the melting and boiling points of water. So basically, somebody called Celsius a long time ago, who got the temperature scale named after him, because you probably get to choose the name if you made it up. He said, why don't we take the melting point of ice as one point in our scale and the boiling point of water as the other point in our scale, and subdivide it into 100 little subcategories. That's all you really need, is 2 reference points if you're going to make a temperature scale. So subdivide it into a bunch of different little categories, and we'll call each of those a Celsius. So we have 1, 2, 3, and so on, all the way up to 100. And then we can take those same temperature changes and bring them all the way down. And he probably didn't know that there was an absolute 0. Maybe he did. And we can bring them all the way up as well. So we got 101, 102, 103. But it's really based off the freezing point and the boiling point of water, right? It's no coincidence that it's 0 degrees Celsius and 100 degrees Celsius. There's somebody made a Fahrenheit scale. If you want to read about that, it doesn't really make a lot of sense, but it is, I guess, kind of interesting to see what they base the numbers off of. A good life hack. Now this is not on the physics course, because you do not deal with the Fahrenheit scale, because it's a nightmare. But we don't deal with it if you just want to know for your day-to-day life. So 0 Fahrenheit versus 100 Fahrenheit. Just if you're out and about in America or some other country that uses it, 0 Fahrenheit, this is a tip that was told to me, is about 0% hot. And 100 Fahrenheit is about 100% hot. This is by human standards, right? It's not the max temperature could possibly be, or the minimum temperature could possibly be. But you can think about it, right? So if you go out in 0% or 0 Fahrenheit, you're going to be really, really cold. If it's like 50% or 50 degrees Fahrenheit, it's going to be so. 60%, you're getting a little bit warmer, If you're over 100 Fahrenheit or under 0 Fahrenheit, you're probably in big trouble. So I wouldn't advise going out in weather. There's probably close to either end of those scales. But it's just a good way to kind of, I guess, cope if you're in an American country. Okay, so anyway, back to our Celsius scale. That's enough of Fahrenheit. I promise to never talk about that scale again. So somebody else then came along, somebody I think called Lord Kelvin, and he decided that that wasn't the best scale ever, because he didn't like the fact that it had negative numbers on it. And he realised that actually there is an absolute 0. There's the coldest temperature that anything can be. And I'm just going to draw a little line here to mark where it is. And he said we should make that 0. So it might seem weird that there's like a coldest possible temperature, but if you think about our particle diagrams, we have all these particles. Let's imagine they're solid particles, so they're all touching each other. These should all be vibrating and vibrating and vibrating. If you heat them up, they vibrate more. If you cool them down, they vibrate a little bit less. So logically it makes sense that we'll eventually reach a point, if you keep cooling them down, where none of them are moving anymore. And that's a temperature that we call absolute 0. So that's at about minus 273 degrees Celsius. That's 273.15 to be exact, but we'll stick with minus 273 for the time being. Both of those are the same temperature, minus 273 degrees Celsius and 0 Kelvin. Fortunately for us, temperature changes work out the same. So if you go up a degree Celsius, you go up a degree Kelvin. So the next point then, minus 272. I don't know why I'm putting this as a minus. Okay, yeah, so if we go up 0, 1 Kelvin, 2 Kelvin, we're going up the Celsius scale the exact same way. A change of 1 Kelvin is a change of 1 degree Celsius. It's just the 0 point is different. So if we want to make a formula for this, we can just think, well, the temperature in Celsius is going to be the same as the temperature in Kelvin. Just take away 273 and see if that works. So for example, if the temperature in Kelvin is 0, then to get the temperature in Celsius, we get 0 and we take away 273. 273.15, let's say, for the sake of being exact, right? And that actually works out because if the temperature in Kelvin is 0, the temperature in Celsius will be minus 273.15 degrees Celsius. So this is a really handy little formula, and you can use that to convert between the two if you like. It is in your log tables what the temperature difference is between them, but just if you want to make a formula, that would be really handy. And you can fill in degrees Celsius or fill in Kelvin, and it'll work either way as your own known. Okay, so now we're on to the blob. So here we got a green blob. You've got a job. It's a paid job. You want to heat up the blob. So if you want to heat up the blob, the amount of energy you're going to need to heat up the blob is going to depend on a few things. It's going to depend on the mass of the blob. So basically how much stuff is in the blob, right? We measure that in kilograms. The amount of stuff that makes them up, how many protons and neutrons and electrons and stuff. It also will depend on how much you want to heat them up by, so the change in temperature is going to be a big factor there too. And a third thing that it's going to depend on is what the blob is made of. What blob made of? Alright, excuse my shorthand writing, but I don't like writing on my iPad very much. It doesn't come across neat. Okay, so it's going to depend on the mass, it's going to depend on the change in temperature, and also it's going to depend on what the blob is made of. Those three things will influence how much energy you need to heat up the blob. So this has turned out terribly. What is going on there? Okay, so I'll just write out the formula. The formula for specific heat capacity is E is equal to M times C times delta theta. E is the energy needed to heat something up. M is mass. C is something called specific heat capacity, just, you know, how much energy you need to heat up a substance by 1 degree Celsius per kilogram. Specific heat capacity and then delta theta is just the change in temperature. So are you heating it up by 1 degree or are you heating it up by 10 degrees? Because it's going to take 10 times as much energy to heat it up by 10 degrees. Okay, now I think it was this slide that I put the calculation for the unit on. This formula is really important. It will be in your log tables, but just make sure you know what the unit is for each of these things. To get the unit for specific heat capacity, we rearrange this formula. So we have E is equal to mc delta theta. We rearrange that to get C by itself. We get E divided by mass times the change in temperature. The unit for energy is joules. The unit for mass is kilograms. And the unit for temperature change is Kelvin. So we get joules over kilograms Kelvin, or we can rewrite this in a more leaving cert way. Joules kg minus 1, Kelvin minus 1. This is one of your index laws. I think index law 5 or 6 from your junior cert says if something's at the bottom of a fraction, you can just put it as a power of minus 1. Meters per second, for example, will be written as meters per second. Alright, so this is how the unit came up with, basically joules per kilogram Kelvin. So that is your unit as well. That's important to know. You don't need to know how to get the unit, but I recommend getting used to that because it'll just mean you don't have to learn off units and be looking them up the whole time. Okay. Slide, I don't know. Right, specific heat capacity definition is not here, but I will do my best to come up with it now. So I know that if I rearrange that formula, I get E divided by M delta theta. So specific heat capacity is defined in terms of energy, it's defined in terms of mass, and it's defined in terms of change in temperature. So the specific heat capacity is the amount of energy I need to raise the temperature of 1 kilogram of a substance by 1 Kelvin. If you look at the actual PowerPoint on Skillgy, you'll see it's on there. So if we want to solve an equation, I'm going to do a separate video on this, to be honest. So just tune in for that separate video. It'll be up pretty soon. Alright, we'll just skip through. And then heat capacity is slightly different. So for example, if I have a metal chair, I'm sorry. I'm so sorry that this is such a bad drawing. Right, I have a metal chair. It's made out of iron. Right, I could be interested in two things if I want to heat this chair up. I don't know why you'd want to heat the chair up, but maybe you do. You might be worried about people burning themselves on your chair if you leave it out in the sun. Okay, so you might be interested in the specific heat capacity of iron, which is the amount of energy needed to raise the temperature of 1 kilogram of iron by 1 degree Celsius or 1 degree Kelvin. Same thing because it's temperature change. So you might be interested in specific heat capacity because that has to do with mass and it's more about the overall substance. But realistically, if you worked in an industry and you were dealing with a particular product, you'd probably be more interested in how much energy is required to heat up your chair by 1 degree Celsius. Not just a kilogram of that substance, how much energy do you need to heat up this chair? So heat capacity really ignores the mass part. We're talking more about objects and less about mass. Heat capacity is the amount of energy needed to raise the temperature of an object by 1 Kelvin. And its formula is E is equal to no M. We do have a C delta theta. We use a capital C for heat capacity because it's different from specific heat capacity. Again, heat capacity now just depends on E, the energy per change in temperature. We don't really care about the mass. This is more about a substance, for a kilo of a substance. This is more about a specific object we're looking at heating up. Again, to get the unit now for our heat capacity, just rearrange that to make C the subject of the formula. Heat capacity is the energy per change in temperature. Energy is measured in joules, and change in temperature is measured in Kelvin. So it's going to be joules per Kelvin. How many joules to heat it up per degree Celsius or per Kelvin. Okay, that brings us on to those set of questions. So we're going to really cover the calculations in the next video. I don't know how long this video is, but I hope it wasn't too long. I hope it's watched. But again, if you do have any questions about stuff like that, just write them down while they're fresh, and then you can come ask me, alright? And I'll be happy to talk to you about it. Okay, thank you for watching. Goodbye.